Okay, we are being recorded. Boy, I can't find any sign that chat's turned off. I'll turn it off and back on. I mean, you know, see if that changes anything. Enable private chat participants. Still looking at the chat stuff here, but not getting anywhere. If anybody has a microphone, you know, you might be able to talk to me.
Mark?
Yes.
So, I got a mic. Is there any chance your chat box is underneath your presentation, or under one of your windows open on your desk?
My chat box is right here. I've been messing with it. I cleared the old chat from before.
We've had some professors or some presenters that have moved their presentation slightly to the one side, and it covered up half the chat box. That's why I was asking.
Okay, let me pull it out of my box off to the side just to see if it'll let me here. Give me a...
Your presentation is kind of centered on my screen.
Okay, well, I've got it in a window, so I can, but yeah, I can't pull the chat. Well, okay, now I just move the chat right on top of the presentation. Does that make it show up?
Yes, it does.
Okay.
Covers up part of your head.
Yeah, that's not important here. We'll see if there's anything important up in this corner. I'll make it a little smaller for now. And all right, if anybody sends me any important chat and it's bigger than on here or whatever, I mean, I can pull it off the side and read it. But apparently I'm having to put it over there so you can get to it. But okay.
What if you stretch that box out and make it almost the length of your screen, but make it real narrow, so it doesn't cover up your presentation?
Yeah, I'll do that. I'm also going to see if... I'm just going to do some resizing here. Okay, can you see it there, the way I've got it now?
Yes.
Okay, so I've got... Is it off the presentation completely?
No, you're on my screen, it's about an inch covering up your presentation.
Okay, well, let me just do more of that then, see if it goes completely off. How about now?
Right there. That's good.
Okay. All right, so I've got it. All right, we'll be able to chat and do. So we're starting a little late, so I will try to get going if that sounds good.
Sounds good to me.
All right. So yeah, this is who I am, and we're going to talk about process engineering. I've called it Part 1 because I cover, I don't know, roughly half of the topics in process engineering, so I don't want to claim I'm covering them all. I don't have expertise in all of them. There's my contact information, or at least some of it. There's an email address there, so if you have questions later, you can email me after we're done here. Just going to place process engineering a little bit. I'm going to go very quickly on these introductions, but you know, it's one of the 5 different knowledge areas that's listed. I made a list here that is rolling off the bottom of my screen, but of how the different areas that I hit on it, and it's primarily in process engineering. Some of section 1, the general knowledge, whatever it's called, common system applications, they call it. You know, we hit some of that area, and some of the facility stuff on ventilation, we hit pretty close to that. It overlaps a lot, so that's some of what we'll be doing. In general, I'd call this unit operations. It used to be in a previous version of the P exam, this stuff was called unit operations. So we look at these common operations in a process: pumping, cooling, drying, evaporation processes, and so forth. The questions beginning the problem is, what unit operation is it? And of course, that comes from experience. So practicing these examples here, practicing old homework problems from classes on these topics are ways to get you familiar. So hopefully you can quickly recognize exactly what things to apply. Carefully rereading the problem. If you go too fast, start off on the wrong thing, be in trouble. So general advice is always valuable. And with these kind of problems, like most of them, starting off with the drawing of the process really clarifies to you what's going on and what you know and what you need to know usually. So, okay, this is a list of specific topics I'm going to cover. I'll just move here. There's a couple of textbooks that are particularly relevant to this. The ones that I'll refer to a few times, in particular Henderson, Perry, and Young, Principles of Process Engineering. Typically, if you took a processing class in agricultural engineering, it would use that textbook. Sometimes in biological engineering, you might use a different, like a Chem E book. Gene Coppolis is the one that I've used. Transport Processes Unit Operations. I'll refer a few times to Gene Coppolis. There may be other chem engineering texts you would use, but anyway, they'd be the basic references for most of these things, especially the fundamentals we're doing. Trying to get down to the basic principles: mass balances, energy balances, which are just inflow equals outflow plus accumulation, whether it's inflow of mass or inflow of energy. The same basic idea. And then there's various specific equations from fluid mechanics, from heat transfer, drying, and so forth. And so as we go through the examples, we'll do mass and energy balances and certain specific equations that come up in the examples. I want to start with a straightforward little illustration and we'll do an example with manufacturing jam. It's an evaporation process, and basically can be solved doing a mass balance. So it's a nice starting place. In this particular problem, we'll give the data kind of in evaporator ease, I'll call it. Try to use the terms a little bit. So it's being manufactured with crushed fruit that comes in 14% soluble solids. Sugar is being added. The ratio is 55 to 45. Pectin is being added. The rate's 4 ounces per 100 pounds of sugar. I'm going to evaporate that mixture until we get up to 67% soluble solids. And so the question, what's the yield in pounds of jam per pound of fruit? Here's the process drawing. I've shown the inputs there on the left in red, and it was the problem was stated as give the result in per pound of fruit. So I've just shown 1 pound of fruit coming in, and based on those specs for the problem, there's 1.22 pounds of sugar if you calculate that ratio we had, 55-45, and then for the pectin, it comes out to 0.0025 pounds per pound of fruit that we've got up there. And then the two outputs, there's a certain mass of water vapor coming off the top of the evaporator up there, and the jam coming out. It's going to be at 67% solids, but we don't know that mass. That's the question. What is the mass of jam coming out there? Okay, so do a total mass balance. Inflow equals outflow plus accumulation. Nothing's being accumulated in this problem, so that term you can see is 0. And I want to try to grab a little marker here. Okay, so here we go. All right, so that's 0. And if you look, I've got 2 inflow terms: the mass of fruit coming in, the mass of sugar coming in, and something's missing there. If you'll notice, think about that a second while I'm talking about the other side. The outflow is the mass of water vapor and the mass of jam. So 2 inputs and 2 outputs. And the thing we've neglected here is this mass of pectin. That's such a small amount, far less than 1%. It's not going to affect the results. There's no sense complicating the problem with an extra term. So I did it that way. Yeah, there's the arrow showing where each one of these terms came from. And we can also do a solids balance because, if I'll back up, we go to solve this. We've got two unknowns here. Over on the right side, the mass of water vapor coming off and the mass of jam coming out. Both are unknowns. So got to have a second equation to solve this. And so if we do a mass balance just on the solid material, we'll find a different equation here. And so same inflow equals outflow plus accumulation, but looking at the solids, we'll have the mass times the concentration. So on the left side, we've got the mass of fruit coming in times whatever the solids concentration is there. We've got a mass of sugar coming in at its solids concentration, and the outflow is mass of jam at whatever concentration it's at. The water vapor coming off is no solids in it. We'll assume that anyway. There's very little solids coming off there. And so all these terms are known. You can see I've plugged in down here the different terms from that, and there if we solve that solids balance, we get the mass of jam is just over 2 pounds per pound of fruit. The mass of vapor coming off the top then from the first equation we did up there is 0.19 pounds per pound of fruit. So that's a look at a very basic mass balance problem. Just to ask you a little question about it. What if this was continuous flow? I mean, typically these things, the input is flowing in at some rate and you get an outflow rate. It's very common to have a continuous flow concentrator, so how does that change the problem? You know, we did everything there, just said there was 1 pound of fruit up there and did everything per pound of fruit. And if you think, I guess I don't have a slide for the answer, but the difference is all 5 of those masses there would become mass flow rates, because if the fruit coming in is coming at a rate, the other things are going to have to come in at a matching rate, and the outflow would all be at a rate. And so all the equations we just did, if this were a rate, we would have done the exact same solution, but all of our terms would have been probably per hour, depending on how it was set up. So it really wouldn't have changed the way we did a problem, other than we'd been talking about a flow rate instead of just a mass. So either way, it was the same basic analysis. And most problems we do in a rate. If you look, I've got 2 examples at the end of this presentation I know I'm not going to get to. I think I numbered them 8 and 9. And the first one is another concentrator problem like this that is continuous flow. It's a more complicated problem. So if you look at that, you'll actually see it with the flow rate. There is slides at the end that you'll be able to see in the PowerPoint. And I also have written up the solution, those last 2 examples that I know I'm not going to get to. I've written that up separately and sent a PDF file that will probably be uploaded tomorrow. I think my email went off late this afternoon to give it to them to upload, so I don't suppose it got uploaded yet, but there'll be both the PowerPoint version and then a slightly separate write-up of the solution, those 2 extra problems there. So I'll mention that while I'm thinking about it. So look a little bit more at mass and energy balances. This is sort of a reference slide. As I go through here from time to time, I have some slides, a lot of information that I want to have in here, so you've got it as a reference, but I won't have time to go over it in detail, so I'll kind of mention what it is, and it's here as reference information. So this is just writing mass and energy balance in general terms, and as we do examples, we'll apply some of it, but it's more of a reference slide that we've got mass flow in. I will mark on it just a little bit if I can find my... So there's mass flow in up there. Find the color. Concentration of what's coming in, and then down here are the terms coming out, an accumulation term. Same general idea down here with the energy balance, where we've got those different terms. But move along. The equations you put together from that is what's supposed to be listed here, and there's a problem, and it was in a whole bunch of these slides. I spent quite a bit of time this afternoon rectifying it in some slides, which is a few I didn't get to. And everywhere I have mass flow rate where I have M with a dot over it, which you can see there, there's this ampersand where I had originally put a dot. So this is supposed to be an M with a dot over it, and another like that. We'll run across a few slides yet, probably. I don't know how many I didn't get to. They're going to look a little funny, but it's the only case when I've got a dot over a term, and I think it's every time a mass term. So we'll still deal with that in a couple slides. I ran out of time correcting them all after I worked on it this afternoon. So, but anyway, these are the general equations you can put together from that previous slide that we just looked at. I can go back here. That's all the terms defined on diagrams. Those are the general energy balance, general mass balance equation. You can apply directly if everything fits, or doing your own balance on typical problems. Just write up your own inflow equals outflow plus accumulation balance. A note down here on the energy balance, I've crossed out that term on the left-hand side where it's mass flow times specific heat capacity times temperature. That is correct only for sensible energy only. If there's no, like moisture evaporation going on, no latent energy. And so if you've got sensible energy only, the equation as it is written, I'll back up. The equation as it's written is applicable for sensible energy only. Just use temperatures. If you have the more complicated case and you look at total energy, enthalpy is the term to replace specific heat times temperature. And so I showed it on that term on the left-hand side, but the term on the right-hand side is the same. If you're dealing with total energy, you'll need to make that same change. And we'll see, should see an example of doing that. Okay, next example I want to do here is look at energy balance problem. This is cooling apples coming in from an orchard. Laid out a specific problem here that's kind of a very large design problem, and then I'll pick out just a couple little parts of that to actually work on. With the short questions on the exam, I think this is somewhat typical of how I have to work the exam. They have to give you small parts of a problem. The whole design problem would easily be an hour worth of something. Actually, this is a larger problem than that. But the little parts would be done in the few minutes that would be typical on the exam. So anyway, so there's 30,000 bushels of apples going to come in during the whole harvest season. 2/3 of it is going to go into refrigerated storage. So we're dealing with 20,000 bushels, not 30. Storage is at 31 degrees Fahrenheit. There's specs here on cooling down to 34 in 5 days. So that's a certain rate during those 5 days, and then from there down to 31 in the next 5 days. So the rate's going to change. So if you calculate cooling rate, it's going to be different during those time frames. There's a rate of 2,000 bushels per day, so you can see that it's going to take 20 days of loading to do that. Ambient temperature 75 at the initiating of loading, but then it declines to 65 degrees over the next 20 days, so it's cooling off in the fall. So every day has a slightly different design temperature, so you've got to keep track of which day you make any calculations at. And the large problem will be to estimate the refrigeration required during the first 30 days as all these changes are taking place. I'll do some examples of a couple little parts of that you need to work that whole problem. Here's a diagram of the process. You can see apples are being carried in there. I've shown on the drawing there the refrigeration that's removing heat from that space. So that's a cue for a heat flow term going out. And then there's number of other terms that are adding heat. Those apples are coming in warm, so they're adding heat, and there's other cases. So we're going to do an energy balance, as we've talked about, and when we do that, we're going to get, in general, that there's heat coming in, term number 1 I've shown up here in the equation, plus all the other terms, however many inputs we can find, and on the right side, all the heat going out, which is probably just going to be one term, that refrigeration term, I think. But we can go through and add those up. I was going to leave a minute or two for you guys to think about what those inflow terms would be, but having started late, I think I want to move on. But it's very much like a ventilation problem on where there's kind of typical inputs and outputs. So here in this slide now, I've drawn those input terms. There's various sources of heat here. If you've got solar radiation, that's this term over here. On this, just like an animal housing building, that's probably not a significant term. You won't have windows. You don't want that heat being added. You don't need windows on the building. But there'll be mechanical energy from lights. If there's lights in there, which people are going to be working, so there's going to be lights. There's going to be respiration, heat load, because those apples are still respiring. Yeah, and there will be another loss because you'll be evaporating moisture, since they contain moisture. So there is another loss besides that refrigeration term. There's just a sensible heat coming in with those apples. There's another mechanical energy term here from people and vehicles that just combines with the light load. There's infiltration of air, and there's actually, of course, air. If there's any air coming in, there's going to be air going out because it's going to displace it. But we generally just treat that as a net term, as an input. So I've written it that way. And there's a certain amount of heat gain just through the building walls, depending on insulation. So again, you should recognize all those terms as typical of building facilities. Very similar situation, with the main difference being there's refrigeration taking it out, which is not going to happen on most animal buildings anyway. Okay. This is a list of all those terms I just went over, so you'll have them in unit conversion at the bottom. These kind of problems, invariably you get some data in BTUs and your electrical data, and a lot of those mechanical loads are going to be in watts, so you've almost always got to go back and forth between watts and BTUs per hour on things like this. Even though I've shown all the terms as watts, the data might very well be in English units. So I just listed that. These are the equations you could use to calculate several of these terms, and so maybe we should talk about that. So the sensible heat load for apples, it's going to be the mass rate of apples coming in. I'll call that m dot of the load times the specific heat capacity of the apples times the temperature change that they go through. And I think in this problem statement we'll see in the next step here, but we're given the problem in a way where we'll look at the temperature change rate on a specific load coming in one day, I think. So where you put the rate in that equation, just depends on what your data in the problem is. The QS term has to be a rate, but how you calculate it, you could have a rate of temperature change or a rate of mass coming in depending on how you're working with the problem. So we'll see that in the specific example. For respiration heat loss, that's going to be fundamental data that you can look up. ASRE Fundamentals catalogs that data for all kinds of fruits and vegetables if it's not given in the problem. And then that's just going to be per unit mass, per pound or whatever. And so you have to multiply the value you can look up times the total mass to get respiration. I already mentioned the mechanical loads like lights and motors. Just you would have to find nameplate information, wattage ratings on all those, add them up. Building heat loss, again, just like in ventilation, you can put all the different parts together into the sum of A over RT. It's the area times the R value, and then that's multiplied by the temperature difference between inside and outside. That's the way you calculate the individual terms. There's some other things I've shown with typically infiltration. We should have a building like this, refrigerated building design, where infiltration is negligible. So I've just crossed that out. Solar heating should be negligible. We won't put windows in and cause that to be an extra load. So won't need to do those. But if we had infiltration, there's the equation. And for your ventilation problems on the facilities area, you'll want to know how to do that, because that'll be the important term instead of refrigeration like we're doing in this problem. Okay, sort of a reference slide for this problem, just definitions of all those terms you just saw on the last slide, so you'll have them. So a specific problem that we can calculate here, given the same data that we already talked about, what's the sensible heat load from the apples on day 3? So that's one term, the sensible heat load of those apples coming in. What is that on day 3 based on the problem statement? Circle the term there. It's being carried into the refrigerated space. And so here's our equation. So on day 3, we've got to know the mass load there. So we wrote the equation out up above. There's 2,000 bushels per day being moved into the space. So on day 3, the third day of that has been moved in there. We'll assume it's loaded when we're making the calculation. So we have it, and then we have used the density that was given in the problem there to get how many pounds that is. So 276,000 pounds is the amount in there being cooled on day 3. And again, there's just a certain amount of understanding the problem statement there. It was specified those apples will be cooling off over a period of like 5 to 10 days. And so all the apples that went in on day 1 are still being cooled at that rate on day 3. The ones that went in on day 2 and the ones that just went in on day 3. So you have to use all 3 days of apples to account for the total cooling load. Okay, then the temperature change was specified in the problem as from 75, the ambient condition, down to 35 over a 5-day period. See, I'm calculating that here, and you see my dot that I was trying to fix. This dot should be over the delta t. So delta t dot is what we're calculating here. So that's the other problem that I mentioned. The other way the problem's going to come out, we were specified in this problem a cooling rate per day. So we calculated the mass load on day 3, not as a rate, but what's actually there on day 3, and our cooling rate is where the rate term comes from. So so we can calculate that. That's from just from the problem specification, and it's 8.2 degrees Fahrenheit per day during the first 5 days, which we're still within first 5 days at this point. And so then we've got the two terms to calculate the sensible heat load from the apples. 276,000 pounds times the specific heat capacity was given as 0.9 BTUs per pound degree F, and the rate of 8.2 degrees per day. And that comes out to about 2 million BTUs per day is the amount of refrigeration that's being required on day 3. And you can imagine the day before that was lower because only 2 days worth of apples were in there, and over the 10 days of harvest, that number is going to go up and up if we were calculating the entire design problem. Just did a conversion here for refrigeration. Tons is common units, so I made that conversion and showed the unit conversion there for your reference. And there's one thing there, I don't know if I haven't seen a chat message yet, but does anybody see I made a little simplification without mentioning there? This is a slight error in calculating. It was on that delta T, the rate of temperature change that came out. Anybody notice a little quick hand waving there? When I calculated that rate, the initial temperature of the apples was 75 degrees, and they're cooled 34 degrees in 5 days. Now I forgot what my little problem is. Let me see if I wrote it on the next slide. Yeah, okay, so the next slide I revisit this. So each day the ambient temperature was cooling off. So I'll back up here. So instead of that 75 degrees, the apples on day 1 came in at 75, but the apples on day 2 came in a ½ degree cooler, day 3 another ½ degree cooler. And so here I've just redone and calculated that average. And so the average temperature of the apples being cooled off in there is 74.5 on day 3. And so the rate is just slightly different, 8.1 instead of 8.2. And so you get very slightly different numbers here, 7 tons even instead of 7.1 I think we were. And so that, I recommend when you recognize very small things like that where it's simpler not to calculate that average, maybe go ahead because you could, I think, pretty easily recognize that was going to be a very minor effect, and you could neglect it. It's also very easy to calculate, but anyway, think about ways to save time as you go along. Okay, here's another example from this on the respiration heat load, where you use just the very simple equation of the respiration. You look up in the table, which I mentioned, Azure Fundamentals Handbook is a place that typically has that if it's not given in the problem. Here it was specified in the problem. And just calculate that by multiplying by the total mass. And again, I need to make up a little time from our late start, so I'll let you look over that, but it's a very straightforward calculation for that simple little equation, but it addresses the respiration part of the problem. So moving on, here's a list of the next kind of examples we'll be doing. So I'll start into that set of examples. Sterilization. Typically, I've been told these are commonly show up on the exam. It's looking at thermal death rate, the kinetics of microbes, where you assume exponential decay according to the usual equation. We use terms like decimal reduction time that we'll define here, and looking at that, and that's the time in which you reduce the number of microbes, the number of spores, by 90%, so 1 log cycle. And when you make that definition, then you get equation here that we can use to evaluate the sterilization process. Thermal death time is probably the most basic unit we look at, and this is the equation for that. T is thermal death time to small case t in this case. There are other terms in there. There's Z value. It's the temperature increase that's required to get a 1 log cycle increase, a 10-fold increase in the death rate. The typical value is 10 degrees C for the botch organism, which is the most common standard. It's going to be 10 degrees C. F0 is the time, and it's in minutes in the standard formulation. The time at standard temperature of 250, that's going to produce the same sterilization as any other temperature you've been given, but the 250 is the standard processing temperature. It's 121 degrees C. Thermal death time is often talked about as a multiple of D, the decimal reduction time that we mentioned on the last slide. And for different cases, sterilization itself is usually specified as 12D as being sterilized. In some cases, which I've labeled overkill here, like baby food, you might go higher than that. Pasteurization is in the range of 4 to 6D, although pasteurization has very specific definitions. There's a couple different definitions that have been used over the years, but it gives 4 to 6D, multiple of D there. This is what the data looks like, thermal death time curve. This is from one of the early works where these methods were developed, sterilization, but this is a graph of the time it took to kill the organisms as a function of temperature This is semi-log plot. If you notice, the y-axis thermal death time is log plot, so it shows up as a straight line on this graph. If you just relate the equation there to the graph, you can see where Z is the temperature for a log cycle reduction on this straight line graph, so like the slope of the graph on the semi-log cycle. F naught is defined as the time at 250 degrees standard temperature. So if you read off the chart 250 degrees, the time required to kill the organisms there is 2.7 in this case. And this is the botch organism, so I think 2.7 must be the F naught for that. It's kind of standard case. You can also plot the decimal reduction time in the same way, and you get the same slope. It still has that slope of Z, but you're graphing something else on the log cycle there, a slight variation of the decimal reduction time, but it's a very similar relationship, very similar equation. It's still an exponential equation, so it's a straight line on this semi-log plot. But I'm going to move on to examples where we use this. So a couple common problems would be to find the new decimal reduction time given a different temperature. Another one would be given a time temperature process that's specified, but you want to switch to a new temperature, find the time it's going to require at that temperature. So I kind of threw in a couple of the basic equations we were going along. This is a slide of different rearrangements of those equations, but mostly there's two equations that you'll be using, and these are just variations on them. But for decimal reduction time, this is a way to express the relation between decimal reduction time at two temperatures. D0 being the reference, T0 being the reference temperature, D0 the reference decimal reduction time, and then D and T being the new or different case, and Z is data for the particular organism that you'd have to have. And for thermal death time, this is I think a rearrangement of the way we wrote this equation before, but again, based on the Z value you have to have for the organism, you'll have the reference. We've written it, in this case it's written out as a reference of 121C. If you were in English units, the reference is 250F, and then F0 is the reference F value, and the T's, circle in both places, T's decimal as the thermal death time. So again, it relates the two different values at two different temperatures when you're making these calculations. Okay, so first example, we're given a D of 0.25 minutes at 121C, which happens to be standard temperature. And if we raise the temperature to 140 degrees C, find D. Our Z value for the organism is 10 degrees C. So there's the equation that I just mentioned. It's used for decimal reduction time. We were given that at 121, it's 0.25 minutes, the value of 10 degrees C. So plug and chug very quickly. Just rearrange a little bit and solve for the D and the new decimal reduction time at 140 degrees C, and we get 0.003 minutes. 140 degrees C is very high processing temperature, and a very, very short time is required. That condition. Another example, we're given the F value for process is 2.7 minutes, and what would be the processing time if the temperature was changed to 100 degrees C? And so here, just note, only F naught's given. No temperature for that is given, so we have to assume standard processing conditions, and that's the 250 Fahrenheit or 121 C, and no Z value was given, so the standard value for Z we have to assume is 18 degrees F, 10 degrees C. Okay, so we'll do the problem based on that. We can solve the equation that you see here, we can also pick the numbers off, since this is all standard conditions, that the results of the equation is right on that graph that we were looking at a minute ago, so we can pick the numbers off the graph just as well as using the equation when we've got standard conditions. Plug them in to the equation, the 2.7 minutes, and the new temperature of 100 degrees C, and we get that thermal death time at 100 degrees C is 348 minutes. Very long process, because that's getting very, very low for a processing temperature, so it takes a very long time if you reduce your temperature that low. Okay, so that's a quick look. If they give you some basic problems like that, hopefully you can plug into those equations like that. Understanding those terms, the calculations are very straightforward. So hopefully you can get those if you see them. Heat exchanger. Next example. Move on to heat exchangers. This is a diagram of a basic tube and shell heat exchanger. There's two fluids involved. You can see there's one fluid coming in here at the shell and exiting out the other side. There's another fluid. In the case of parallel flow, the way we've drawn this, that fluid is going to enter on the left and flow parallel to fluid B. We could have counterflow if it were coming the other way. And for the way we're going to problems you'd be doing, we're going to look at, it's not probably going to really affect the problem whether it's parallel or counterflow. You get the same basic analysis in either case. And this equation down here shows the kind of the basic analysis of the problem. The overall heat transfer, Q, in a heat exchanger like that can be calculated as U, the overall heat transfer coefficient, multiplied by the effective area, the area of the exchanger where the two fluids are touching both sides of the exchanger. There's a certain amount of area there, effective area, and then whatever the mean temperature difference is across the two sides of the exchanger. Based on heat transfer analysis, is very obvious, statement that whatever your heat transfer coefficient is times the area in that exchanger times whatever the average temperature difference is. That's basic equation. I've rewritten the equation now where I've written as delta T Lm. So you may remember from heat exchangers, that's a log mean temperature difference. Because in basic heat exchangers, a theoretical analysis shows that the correct average is just the log mean average. So you can calculate your average that way, and there's that equation's been derived for those, and we'll list it here. Okay, so here's the drawing with the equations added, the new equations added. The first equation listed up here is the same one we just talked about, and now here's the log mean temperature difference, and I've written three different approaches to calculating it, or slightly different approaches, or almost the same. But the first definition there, the log mean temperature difference is delta T max minus delta T min divided by the log of the ratio of those two, delta T max over delta T min. And the definition of delta T max and min is shown up on the diagram now. So on the left-hand side of this exchanger, you're going to have a delta T. It might be the larger, it might be the smaller. And on the right-hand side, there's also a delta T. And if one's max, the other is going to be min. And so in any given problem, you do a process drawing like this and evaluate the temperature difference between the two fluids on one side of the exchanger and the temperature difference on the other. Just as a note, that's the temperature difference between the two fluids. You could also define a delta T for the fluid itself. It changes as it goes through there, but in the log mean temperature difference, that's not what we're talking about. We're talking about the temperature difference between the two fluids. The one difference that's larger is delta T max, and whichever one is the smaller, and it's delta T min. And when you use that definition, delta T max and min like that, you just have one equation that applies to both the parallel and counterflow case. Another way to define those, and I'll say that this definition is the one you'll see in Henderson, Perry, and Young. If that's the reference you use, that's the way you'll see it presented. But the other way, instead of defining it max and min, is just to say there's a cold side and a hot side. And when you do that, then you get different equations for the counterflow exchanger, slightly different than for the parallel flow exchanger. So if you're looking up this equation in your reference, it doesn't much matter whether you've got the simpler delta T max and min or not if you're just looking it up. I prefer the delta T max and min because it's so simple. I can memorize it. I don't even have to stop and look it up. Even after all these, after a long time, I still remember it. So one way or the other, depending on what you're used to, you got to calculate the log mean temperature difference for a lot of these heat transfer problems. And then another equation down here. This is going to be required in a lot of cases. Now I am talking about the temperature change for the fluids. The delta T's in this equation, delta TH and delta TC, are the hot fluid and the cold fluid. And all these definitions are on the next slide. So I have a definition slide on the next page. So so you can evaluate the energy being taken from the hot fluid and going to the cold fluid, and they have to be equal. If you think about it, that's assuming there's no loss from this heat exchanger. All the heat that leaves one fluid goes to the other. So those two terms can be equated. Gives you another equation that you'll need sometimes in the analysis. And I have a new slide here. Sorry, I have a duplicate slide. Oh, duplicate slide, reduced it to just the simpler version of the equation, but it's the same thing. There's all those definitions. I said they were in a slide there. So there they are. Yeah, we're about halfway through the presentation. I'd put this in here to take a break. So we're only 6 minutes behind right now, so we're close to catching up. I think I'll make it about a 1 minute break since we are behind, but I'll stop talking for about 1 minute here, and then I'll start back up just really soon. But you can take a quick break if you want. I'll be right back. All right, I suppose our minute is about up here. So I'll maybe start back to it here. I notice I haven't seen any chat while we're on our break. So somebody told me Maybe I have the chat set wrong. Yeah, if anybody wants to, while I'm messing around here seeing if I've got something messed up on chat now. If you can chat, send me a chat message and just say so. Enable. I'm not going to spend much time on this since we... Okay. I had my chat window messed up, so I hadn't seen any of these chat questions I've been getting till now. I have several. Let me take a quick look. Let me go through them really. Hopefully, I can just answer them really quick. There's a question about: am I assuming that the apples from day 1 and day 2 haven't cooled? And that problem on day 1 they cooled a certain amount for the definition. On day 2 they did. On day 3 they're still cooling. So we included 3 days worth of apples, but we only included the cooling rate per day. So if you look at how that problem is set up, on day 3 they were cooling at a certain rate. We were just looking at that rate and what was going on day 3. And it's kind of because the way we kind of did that problem with the mass of apples, not a rate of apples, but we did the cooling rate as a rate, not just a full temperature change. So we'll look at that. Hopefully that's clear. Linear temperature decrease. Yes, we did assume a linear temperature decrease. From the problem statement, you can see where we had that on those apples. Can't seem to find it in Principles of Process Engineering. So from Paul D, I don't know what we were talking about at the time, so email me that question afterwards so I'll know what it applies to. Is the death time chart in the Process Engineering book? The death time chart is not in the Henderson, Perry, and Young. I don't think it's in Genecopolis either. This is a specialized topic. You'd find it in food. How about now? Did anybody get sound back? Okay, so I've got one. We have sound back. Is that okay? Sounds like we have sound back. Not quite sure what happened. Although I yanked my wire, I think, and I got it plugged back in. The reference for sterilization. Okay, yeah. The question
Mark, if you can hear us, we lost sound again.
How about now, people? Are you hearing me?
We can hear you.
Okay, thanks. Maybe some of the sound questions came in after other people said it was back. So, all right, I better get going. Um, so this is a list of reference ideas. I've mentioned most of these already. Azure Ray Fundamentals has a lot of basic data. Processing text we talked about. ASA EE standards, probably heard about before. And upcoming examples, I'll refer to some of the specific standards particularly applicable. And there's some other texts there that are got a lot of related information. There's one in particular, this Lower et al. Lower is it's an on-farm drawing book that has some really handy psychometric. You'll see an example. Midwest Plan Service has got a lot of basic data. I'll refer to that in example. Yeah, some ideas for studying. Um, I actually forgot to look this year if Amy did the uh, webinar on study tips. Old, go back a few years in the archives. There's webinars on the topic of economics and statistics by Matt Lima. It's another version. So there's a couple places for a lot of ideas. And again, specific questions for me, you can email as you're studying later on. This is a list of a few specific standards that I think are important. Again, I'll mention those as they examples. This much. And I don't think there's a lot of other ones besides the one I mentioned. Okay, so we were looking at heat exchangers. Here's the equations again in the setup that we just talked about. But I want to move on to an example. We've got some kind of liquid food material. It's got a specific heat capacity given there. Inner pipe heat exchanger. It enters at 20 degrees C. It's heated up to 60 degrees C. Flow rate's a half kilogram per second. Hot water at 9 degrees C is being used. Counterflow. Flow rate's 1 kilogram per second. Calculate the exit temperature of the water. Basic problem. It says assuming steady state conditions, the equations we've looked at and the
We just lost your sound again.
How about now? Did we get the sound back? What have I got going on here? Anybody? Okay, you got it back. Okay. I just, once I lose it, it seems to come back when I mute and unmute. I know when I lose it now because I've heard that it gives me a beep. So if it happens again, hopefully I'll be able to get it back quickly. Okay, so we're looking at the solution to this one. All right. I'll back up to, again, this is the problem specification. For a heat exchanger problem, we went over the equations before the break. So we specified this food being heated up. It's coming in at 20 degrees C, heated to 60. There's flow rate specified for the food and the water. The temperature of the water coming in is specified. And so if we look at a diagram of all that information here, up here in the corner, so those are the temperatures, the food going from 20 degrees to 60 degrees C as it goes up through the heat exchanger. The water is cooling from 90 degrees to an unknown temperature. And if you remember the equations, the third equation we looked at was just equating the heat gained by one fluid to the heat lost by the other. That's the equation here. Putting subscripts here, F for food and W for water, because we had food and water in this problem. And so just by equating the heat gain, the heat loss, in this case with only just that one temperature unknown, we can solve the equation that way. There's one unknown, and here is the temperature of the water at exit, the hot fluid, THO for a hot fluid. And so just plug in the mass, the flow rate of food, the heat capacity was given for that, the temperature change for the food, the mass flow rate of the water, the heat capacity of the water, and the initial temperature of the water. And you can calculate very quickly 71 degrees C should be the exit temperature of the water. So that's the kind of problem you hope to get, because you simply have to understand the definitions and the terms, and it's a very quick calculation to get the one missing temperature like that. The next example, let's just go a little further with that problem and find the amount of area you would need in the heat exchanger if you had a heat exchanger with this heat transfer coefficient. And actually, this very easily could have been the original problem, and you would have had to, as a first step, calculate the temperature we just calculated. But here's the data. It's, again, the same problem, so this is just a restatement of the same data we just looked at, but we're just asked for some more information. Looking at those equations, we had the most fundamental equation, overall heat transfer coefficient times the effective area times log mean temperature difference, and we were asked for the effective area in this case. The Q in here is an unknown initially, a second unknown. We can calculate that. If we go back to the other equations that we looked at with the heat leaving or being gained by one of the fluids, and this is approximately that equation. It's got the ampersand problem, but it's because that equation was mass flow rate of the cold fluid, so this should be m dot C right there. But recognize that equation from the other slide, so we can put those two equations together, or so that I went ahead and solved the equation on the right there. I solved it for Q, and then we can substitute that in the first equation on the left. But substitute those terms in, and we get that the amount of heat transfer from one fluid to the other is 80 kilojoules per second, and that's the same amount of heat transfer then we have to have across the heat exchanger that will help us define the effective area needed. To use that first equation, then we've got to do log mean temperature difference. I went ahead and calculated it kind of separately here. Instead of plug it all into as a big equation. But I use the delta T max and min terms there, and I think okay, sorry. So if you look on the right-hand side of this exchanger, the temperature difference is 71 minus 20 degrees, which is larger than the 90 minus 60 on the left. So delta T max is 51. It's 71 minus 20. Delta T min is 30. It's 90 minus 60. So plug those in for delta T max, and again, I find that a pretty quick and easy way to get the log of mean temperature difference instead of using the other definitions. It's about 40 degrees C. Plug that in now to the equation up here. Plug that number in, and remember there's a little unit issue in here because we've got watts and we've got kilojoules per second. So kilowatts, in other words. So we got to make sure we get the 1,000 factor in there. So I put in 2 kilojoules per second to match the units, where we had 2,000 watts specified. And as long as you get the units right, then you'll see effective area is about 1 square meter in this case. Okay, so now we've used all three of those basic equations in kind of a couple common ways there for heat exchanger problems. Heat exchangers, there's kind of a little more advanced steps in heat exchangers. The slide got converted a little funny, but the next level of complexity is to use effectiveness ratio. It's pretty straightforward. I would say if you kind of remember that and consider this kind of in your area especially, you might want to review it because effectiveness ratio use might come up, and it'd give you another problem you get. It's not real complicated, just slightly a little additional information. You have to have the charts, but they're in Henderson, Perry, and Young. I've given the page numbers right there where those charts are. So if you want, you can review that, go to the next level on heat exchangers. And remember, when you do that, if you have one fluid at constant temperature, then you need to use oftentimes the effectiveness ratio method. And in that case, the R that's defined in that effectiveness ratio, that goes to infinity. You'll see that on the charts and how that works. If that's a special case, you can generally use the effectiveness ratio method for that special case, recognizing that R goes to infinity if you've got a constant temperature. A constant temperature is going to occur if one fluid is either evaporating or condensing. Then there's a constant temperature. So, and the last equation down here is an even more complicated look at heat exchangers that shouldn't be on the exam at all. I have a background in mechanical engineering, and it was probably, I think it was on my exam, but shouldn't come up in this exam at all. So don't look at that one. But effectiveness ratio, it's in Henderson, Perry, and Young. So the fact that it's in Henderson, Perry, Young means it's fair game for the bio ag engineering PE exam. Okay. Next topic we have mass transfer between phases, and so humidity, evaporation issues, drying issues. The fundamentals of that, one of the fundamentals is going to be psychometrics, because there's going to be air involved, and that moisture is going to be condensing out of the air or evaporating into the air. So pretty sure you've covered psychometrics in some of the other presentations, or maybe again in one coming up. I'll do examples where we'll do some psychometrics. I won't just go over the fundamentals, except give my really short version of the fundamentals here. If you look at this skeleton psychometric chart I put down here at the bottom, I've drawn 3 lines on there just to indicate the basic idea on that chart to keep in mind as you're using it. If you've got a process going on that's a horizontal line, moving either left or right, like this arrow down at the bottom, that's sensible heating or cooling, depending on whether it's going left or right. It's a sensible temperature change when it's a horizontal line. because the y-axis of the chart is moisture, basically. So horizontal line means only sensible heating and cooling. The vertical line over on the right, in theory, that's pure humidifying or pure dehumidifying without a sensible energy change. It's not a common process, but the concept is important to realize that the vertical line on the chart, that's what's going on, because the y-axis is basically moisture content. It's humidity ratio, you'll see on the y-axis. And so that's a basic concept. It's not a basic process that you see. The other process you see is evaporative cooling, which is exactly what happens in drying processes. And that's the topic that we're on right now. And so that's the diagonal line you see here, and as hopefully remember, that's following a line of constant wet bulb temperature, because the evaporative cooling process or drying process, the air moves up and to the left along a constant wet bulb temperature line. And so we'll work on the examples with that, but that is my most basic summary of psychometrics and the basics of what's on that chart. So here, again, I've drawn the drying process right here and labeled that as a line, a wet bulb line. So in grain drying, food drying, these psychometric issues come up. Also, moisture contents of the materials is going to be involved, because you're either drying or wetting the material. There is ASAE standard D245.6 is moisture data for that. We'll see in the examples. Moisture is going to raise the issue of whether it's wet bases or dry bases, so we'll have to keep that straight. I'll look more at that. And then with a lot of these drying problems, air is being blown through the material, the drying air, warm, dry air typically being blown through the material. And so the question of airflow resistance and how much airflow, what kind of fan size you need for that, comes up along with it. And so those are the issues that are going to come up in drying problems. So we'll look at some of those. Equilibrium moisture content. It's illustrated on this chart. If you've looked in like the ASAE data, equilibrium moisture content, you should kind of recognize this chart. This is kind of just part of that pulled out for corn. I've shown the equilibrium relationship at 3 different temperatures, 0, 20, and 40 degrees C. X-axis is relative humidity, and y-axis is equilibrium moisture content. That's a fundamental relation. Because of the vapor pressure in the material and the vapor pressure in the air, they come to equilibrium. And as humidity or moisture content changes, you get this relationship. And it also varies with temperature, as you can see. At a given temperature, you get one relationship. Different temperature, you get a slightly different relationship. And what happens if you look at this, if you've got a material at a given moisture content, in this case, say 15%, as you move to the right across here, at a low temperature, you get one equilibrium humidity. As you move up to a higher temperature, so from 0 to 20 degrees C in this point, the moisture of the material may stay the same, and your equilibrium relative humidity is going to go up. It's just the basic relationship in these materials. Yeah, I've listed in drying problems, if any of the common grain materials are involved in the drying problem, there's 2 choices how to get the data. That ASAE standard, and I should not make such a big deal about this probably, but if you want the constants to calculate that, there's an equation in there, and you can calculate it. And I made this slide. I was thinking about the fact that the newest version of the standard doesn't have a good way to take the constants and make calculations, because it gives 100 different versions of the constants. You don't know what to use. But it does have charts like the one we just showed, and so you can use those charts and pick numbers off the charts. They're not really accurate, but they're probably just adequate for making calculations. So you should be okay using D245.6. If you have this reference book that was listed there, Lower et al. 1994, it's a grain drying book. It's got psychometric charts in there that are already have that information for equilibrium moisture content plotted on the chart.
and it saves you a step. You're going to be using the cyc chart anyway. If you have those cyc charts, you don't have to go look up your equilibrium moisture data. So it's a preferable method if you either have that book or you can get copies of those charts, and you'll see those in the example I'm fixing to do. Otherwise, if you use the ASAE standard, you can use the little graphs that are in there, the graphs that look like the chart that's underneath here that we're just looking at. And you can pick numbers off there to, I think, just barely enough accuracy that you're going to be okay. So you're okay with it. You just have the extra step of picking them off the chart instead of having them already plotted on the cyc chart. We'll see this. So this is what a psychometric chart from that book looks like. If you look at the curved lines, the relative humidity lines, if you look closely here at the chart, there's two different sets of curved lines here that look kind of like that equilibrium moist. Looks like the humidity lines, and those are the equilibrium moisture lines. So 18% equilibrium moisture, and this is specific to hard wheat. Each chart's specific to a particular grain. So that's the line there. It looks almost parallel to a relative humidity line, but not quite. Okay, so let's go on to look at actually using this. Remember the drying process we talked about, it follows the line of constant wet bulb, and the air is coming into the dryer at some initial temperature. That's this T naught down here. It's coming at some initial relative humidity here, and so that defines the point where the air starts right down here, the temperature and relative humidity. It's going to follow the wet bulb line up and to the left until it comes to equilibrium with whatever grain or whatever other product is being dried. And so this is the line of relative humidity, and this is the point where it intersects that line, so that's the ending point of the drying process, and it tells you what the temperature is of that material. As it dries, it's going to be forced into this equilibrium temperature, T sub G. And so if you know that equilibrium relative humidity from the data as we talked about, then you can look this up on the cyc chart. If you have the special cyc charts, the moisture is plotted directly. You don't have to go make that one lookup before you come back to the cyc chart. This is showing those same values in the previous slide. I'll go back, but those temperatures, the initial temperature and relative humidity of the air, the final temperature of the grain, the equilibrium relative humidity, just showing those values, how they relate on the equilibrium moisture charts. The equilibrium, there's two different equilibrium relationships. There's one at the initial grain temperature, T0, or the initial the air temperature. Sorry, that's the initial air temperature, T naught. And then there's the other relationship that occurs, the temperature of the grain, because of this drying process, gets forced to TG. It's a result of the evaporative cooling process. And so some of the relationships are at that temperature. And so looking at the chart, you got two temperature involved, but given the relative humidity of the air, if you read it, the temperature for the air, you get an equilibrium moisture content off. You're also given the initial moisture content of the grain, so you read over here at the correct temperature, the TG temperature that you have to calculate from the cyc chart to get it, and that tells you the equilibrium relative humidity that the air has to end up at in that process. So it's the same data in the previous slide that was shown on the cyc chart. Here's how it looks on the equilibrium moisture chart, all those same conditions. Before doing an example, here's a few more things about drying. If you've got more than just 2 or 3 layers of food material or grain kernels, in this case, you're going to get what we call a deep bed process. Not all the material in there is going to behave the same. If it gets more than 2 or 3 layers deep, it becomes a deep bed. There's variation along that thickness, and so it's a more complicated problem. We'll look at both cases, but that's the more complicated and the more common problem a lot of times for calculations. More likely to get problems on that. But dehydration of solid food materials is the same process as the grain drying process. Roughly speaking, it acts like multiple thin layers, multiple individual layers, but you don't really make calculations based on that. But that fundamentally is what's going on. So I've listed a couple more fundamental equations here. This is just the two relationships that go back and forth between wet bulb and dry bulb temperature. See them right here. This is wet bulb and dry bulb. Wet. Okay. I'm going to back up here. Wet basis moisture content and dry basis moisture content. Okay. So you can use these relationships. You may have those recorded already. The other equation down here is a very common one. I'm pretty sure I have this in an example, but this is a very common one down here. If you have to calculate the amount of moisture to be added or removed to material from either drying or rewetting it, so typically moisture removed, you have to calculate that amount of moisture removed, or calculate the weight change during the drying process, which is the same thing. Weight change is the amount of moisture removed. If you have to calculate that, this relationship is usually the easiest way to do it. A lot of times you can go about it, take 2 steps or something, but you can, this one equation right here is very effective for that. It's just that W1 here, it's the mass at 1 moisture content, and times 1 minus that moisture content as a wet basis is equal to the same values for the second moisture content, the second mass you get over there for that. The unique thing about this equation is those moisture contents are wet basis. Most all other equations with moisture content are usually on a dry basis. Dry basis is a non-changing basis, and so when you're making a theoretical calculation, you usually end up working with dry basis moisture content. But this particular equation works with wet basis moisture content. So if you use it, you got to keep that straight. And the reason is 1 minus wet basis moisture content is equal to dry matter content. And that's what doesn't change during the process. The amount of dry matter before you dry it and after you dry it hasn't changed. Only moisture has changed. So that's why this equation is kind of funny compared to most all the other ones that use dry basis moisture contents. And then one more thing about those moisture contents, the equations other than this one are almost always in dry basis. Industries almost always measure and talk in wet basis. So you very frequently have to go back and forth and make those calculations between wet and dry basis because data is very often wet basis, equations are very often dry basis. So be prepared for that. And in fact, I would say if you're given any problem and a moisture content specified, I mean, they'll probably say dry or wet basis, but if they don't, you should assume wet basis because universally industries of all kinds use wet basis. So if you ran into that, you'd have to assume wet basis, I think, unless there was some reason that there's some indication it's a dry basis moisture content. So just a little bit more, the thin layer process, I kind of mentioned, is not nearly as complex. You can just use this simple equation. There's various equations, but the most common, the easiest to use is usually the Page equation. It's a simple exponential equation. There's the ASA standard 448.1 that gives the data for that equation for different. That's going to be, I think, all grain products in there. And it looks like this slide got kind of wrapped around a little bit. But anyway, you can look up the constants in there and use that equation. And it's if you're given that equation, if you're given a problem in thin layer drying, it's just plug into that equation and calculate the missing term. So I'm not sure I actually have an example. That would be a very straightforward thing to do. You'd either be given a moisture content and calculate time, or you'd be given a time, you'd calculate moisture content with that equation. To calculate moisture content, it's in terms of moisture ratio. I use MR for that. It's just like temperature ratio or dimensionless temperature you'd see in heat transfer. Got written over a little bit here in the wraparound, but I think you can still see the definition there. It's just actual moisture content minus equilibrium moisture content divided by initial minus equilibrium moisture content. Again, completely analogous to dimensionless temperature you'd see in heat transfer. And again, in this equation, like most equations, it's dry basis moisture content. So with that, you should easily be able to calculate any thin layer question you're given. But deep beds are a little more complicated. This is a little more fundamental look at the way the thin layer process works. You may hear that they may use the term falling rate period. If you've got a drying process it's going to be in the falling rate period. If usually that's going to be the normal, and that's where the thin layer drying equation, the Page's equation, applies. There is a constant rate period that can occur in some materials. That only occurs when materials literally have liquid moisture on them. And so if you've got some kind of fruit or vegetable that's drying, it starts off with liquid on the surface. It'll dry at a constant rate as long as that liquid's on the surface, and it's an evaporative cooling process. Again, evaporative cooling and drying processes are about the same. If you've got free liquid on the surface, the equilibrium relative humidity is 100%. But for materials that don't have free liquid on the surface, the equilibrium relative humidity is something less than 100%. And in that case, you have the falling rate going on. The drying rate is slowing as it dries down. So if you got liquid water, it's an evaporative cooling process. You can do evaluations on the site chart for an evaporative cooler. You end up at 100% humidity instead of ending up at some equilibrium relative humidity. And so, but for drying problems, unless it's specified, something's weird, you've got liquid here, it's not specified, a drying problem is probably going to be talking about the falling rate period. So you could use the Page equation that we mentioned, or the deep bed analysis that I'm going to do here. So, yeah, and we'll see as we go through these problems. If you've got a falling rate period, then it's not just an evaporative cooler. You've either got to know that equilibrium relative humidity based on having the site chart or having the ASAE data, or the problem would just have to specify what the exit conditions are in the dryer. If it were specified in the problem, the temperature, humidity, some way of what's exiting the dryer, then that could tell you what you need to know, and you wouldn't have to have equilibrium in that case. So again, if we get to the examples here, we'll see that. One more note on water activity, designated ACE to W. If you've worked in the food engineering area, you'll hear this term a lot. It's the same as the equilibrium relative humidity I've been talking about, except it's on a decimal basis. Equilibrium relative humidity is expressed as a percent, like other relative humidities are. If you express it as a decimal, and if you're dealing with food, you'd go from percent to like this one, 0.85 AW, 0.85 water activity. But otherwise, all things are the same. And so if you're dealing with the food, they may use the term AW, and it'll have a decimal instead of a percent. And there is one little point I think I put on here. In terms of food, something that might be worth a point on the exam, if you look at the FDA regulations on sterilization of food, any food that's less than or equal to AW of 0.85, which is 85% relative humidity, those are not subject to processing. They are considered sterilized by being that dry below that level of AW. And there's a specific, in the Code of Federal Regulations, specific ones that would cover the material, and they specifically says in this case it's not. So it's when you start dealing with water activity and drying foods, this is an important little fact that you might want to know. So remember that as you go through. I've got some examples on grain drying. These are just a list of bulk densities. They're in AS. If you need bulk density, they're in this ASAE data, 241.4. Okay, it's going to evaluate kind of a basic drying process, which is going to be a moisture balance, or a mass balance. The amount of moisture that's removed from the material has to equal the amount of moisture that comes into the air. So I've defined the terms on this slide. There's a mass flow rate of air down here. It should be m dot sub a. We've got the ampersand in here again. But, the humidity ratio of the air coming in is this value. It's got a different humidity ratio coming out. So that is going to define how much air is added to the air that's doing the drying. The material in there that's drying, grain, I've listed here the change in moisture content of that grain is going to be the same amount of moisture. It leaves the grain, goes into the air. So you can equate those two things, make sure you get the units right, and you'll get the mass balance for the amount of moisture being removed there. This slide kind of illustrates how that process changes. In this deep bed process, it changes as you go along. So you got to be careful what the terms are. So you can see here. So early in the process, over here on the left, the humidity ratio of the air coming in is this value, omega A N. Late in the process, we're assuming this isn't changing. Most any problem is going to be constant conditions that I think you'll see. So that doesn't change. It's always the same. But the outlet from a deep bed dryer is going to change. Okay, and there's a problem with this drawing. Let me make a little change here real quick. Give me a second. Okay, I want to write right here. Wet. So this material up above where it says drying is still wet. It should be. Should have been like the other one. So like over here in the second drawing, up at the top, there's some wet material. It's a different color to indicate it's wet. And all this material over here in this first drawing is wet, and it should be that different color. But I think it ended up in the drawing being behind something. So similarly, there's the very bottom material is dry material. So again, like on this drawing at the bottom, it's labeled dry. Yeah, we need the same thing over here. So dry material. Okay. So now the left-hand drawing is more correct. But anyway, as I said, the inlet condition is not changing in here. We've got some humidity ratio coming in. When early in the process, when the grain is the upper grain is still wet, we have some outlet humidity ratio equivalent to the wet material. As the drying process moves along, the amount of wet material up at the top decreases and decreases. Somewhere in the middle of the process, it disappeared. I drew an intermediate step here where there's still just a little bit of fully wet material at the top. But as you can see, it's about to disappear. And so later in the process, as things are drying, the material at the top is not completely wet. It's partially dried. And when you get to the very end of the process, at the very end of the process, that becomes equal to humidity ratio for dry condition. So anyway, that difference, if you have a problem and you're talking early in the process and the material at the end of the dryer, the top of the dryer is still wet, then you've got this relationship here. As you get later in the process, you may not know the outlet condition, and so you may not be able to make a calculation at all without doing what I call a deeper analysis. So we'll look at a problem and how that plays out, and in the analysis here. I said you could do that analysis based on those, just remembering that the outlet condition can be something different at different times. You always need to remember that with a deep bed dryer. Some cases you know the outlet condition, some cases you don't, so you won't have that value to use. If you equate those, this is the equation you should end up with. On the air side, you've got a mass flow rate of air. On the grain part of this material being dried, there's just a certain mass here being dried. It's not a rate. And so you've got time in here on the air. Depends on how long you blow on that air. You can see that we get the units right. I've shown the units here now. You can see that we've got kilograms of water on the left and kilograms of water on the right. We've equated the amount of water leaving the material to the amount of water being picked up by the air. If you solve that equation for time, if that's what you want to know, this is what it looks like here. And so if you know all those values, the moisture content difference for the grain, the humidity ratio difference for air at the inlet, air at the outlet, um, and you typically are going to know a mass flow rate of air and a mass of grain material. You can just calculate a time. But just realize it assumes it's constant outlet condition. It assumes that initial condition it's true initially, but that changes during the process. I suspect though, if you get a problem like this in the exam, there's a good chance it'll be early in the process when you know this condition and you can use this simple analysis. Henderson, Perry, and Young has the more complicated analysis where you look at deep bed drying and how that varies during time. Again, if this is your specialty area, you might want to review that. There could be one problem on an exam. I'm guessing it's not your specialty area. It's not something you want to go try to learn probably. But this simple equation up here at the top, if you know constant conditions, is very easy to use. You just need to know your definitions there of the amount of moisture content of the grain, the humidity ratio of the air, and you can use that. Okay, an example here. So we're looking at drying wheat, in this case kind of a little unusual, but drying wheat. We want to dry in general 18% to 12%, batch grain dryer. So that's kind of what I've been drawing in the previous illustrations. We're going to dry until the top layer of the grain reaches 13%. Ambient conditions here, 70 degrees and 20%. So that's really that T naught and RH naught that we talked about when we were setting up the definitions. We're asked for two things: the exit air temperature early in the drying period. So I was just talking a lot about that early in the drying period. You know the conditions, and you can be sure of the conditions. Determining the exit air humidity and temperature at the end of the drying period. Now that depends on the problem statement. In this case, we said we're going to stop the drying when the top layer reaches 13%. So we've specified what's going on at the end of the drying period. So in this particular problem, we know what's going on because it was specified. It's at the case of 13% moisture at the top of the dryer. So we should be able to make that calculation too, just like we can always make it early in the drying process. So this is where the easiest way is to use the chart out of Lohr et al. The skeleton chart again looks like this. You've got initial conditions and goes up to the equilibrium condition here. And let me just look at that on the here it is plotted on the actual site chart out of Lohr. Initial conditions were 70 degrees Fahrenheit, 20% relative humidity. We follow a constant wet bulb line, as you can see up to here's that's a constant wet bulb line until we're in equilibrium with 18% moisture. Wheat was specified in the problem at 18%. So early in the process, the top of the grain is still completely wet at 18%. The exit conditions are going to be in equilibrium with 18%. And so on this chart, we can just find the 18% moisture line and determine the exit temperature is 53.5. That's the value we were calling Tg in the definitions, T sub G, 53.5 Fahrenheit. And again, if you're not using this chart that has moisture content plotted, you would have to go to the ASA data and look up what humidity, equilibrium humidity you had at this condition right here. And on the chart, you can see it's just above 80%. So you have looked it up and found something around, looks like 83 or 4% relative humidity, and you could have found the point the same way after you look that up in ASA data. Now there is a problem here that it's an iterative process. You have to know this temperature to know where to look it up in ASA data. You have to know the T sub G value. But if you look at this process, you can estimate on almost any drying problem roughly where you're going to end up. You're going to go up the wet bulb temperature line. You can go up this line in this direction to some high value. You won't go quite to 100% relative humidity unless it's an evaporative cooling problem. And so you can estimate very easily about what T sub G is. Go to ASA data if you don't have the site chart. Go to ASA data and find this value. And you usually don't need to make a second iteration. Because there's just not a lot of variation in what humidity you're going to end up at. 90%, 80%. It's not going to change the TG value very much. And so your initial guess for that value that you go to ASA data with is probably going to be accurate enough. You don't even have to do a second iteration. But in any event, when you do use ASA data, you might have to iterate if you make an estimate here and you've got an odd problem and your final humidity was nowhere near where you estimated. So, if you have the good psych chart, it never comes up. One more part of this problem I'll try to go over. So we're asked for, at the end of the drying period, to find the exit air temperature. If we draw that on the chart, it's the same basic idea. The air's for this whole problem is coming in at 70 degrees Fahrenheit, 20% humidity. It's a drying process, so we're looking at going up this line of constant wet bulb until we hit the equilibrium condition. In this case, we were told that we're looking at the end case where it's 13% moisture content, so we can find the intersection with 13% moisture content right here and find the temperature at that time. At the end of the process, the temperature coming out is going to be 58 degrees. This would be a case if you're working with ASA data, you're not up near 80-90% humidity, you're at a lower humidity because the grain's actually dry at this point. We're looking at the end of the process, so it's a little harder to estimate this temperature as accurately. So you might have to do one iteration step if you were doing this problem with ASA data instead of the site chart from lower. But it's a process. It's just that drying process follows the line of constant wet bulb temperature, just like evaporative cooling process. So the other thing I have in here, we've hit 8 o'clock. I had an evaluation of the cooling process because you can be drying this material or cooling it. So you do the same kind of balance for energy in the cooling process. We had a drying process. We did the mass balance, do the same kind of balance on energy. Look out for my ampersand here where we had another M dot that didn't get done, and you get this energy balance just like the mass balance we did for moisture. It's got these temperature changes in here, temperature change of the air going through the cooler or the dryer, whatever you want to call it, the temperature change of the grain material. And in both cases, they're multiplied by the specific heat capacity of the material, the air in this case, the grain, and the right-hand side. Again, this is just sensible energy conservation. The fact is, this almost always occurs with moisture change. Even if you're only trying to cool, you're going to incidentally be doing some moisture change. And so this balance will be an error if you use only a sensible energy balance. But if you go on here, you can do a total energy balance. Instead of using temperature times specific heat capacity, you use an enthalpy. So the air will now have an enthalpy change to get total energy in the air. The grain equation hasn't changed because the temperature of the grain is a sensible energy change process. The latent heating effect is in the air. The temperature change of the grain is a sensible process, so you don't account for the humidity a second time over in the grain. It's accounted for here in the air. And again, this term is just M mass flow rate of air. M dot A is the messed up term here. And again, it looks just like the moisture balance that we spent time on, but it's energy in this case. You can do the analysis for temperature change here. Let me just see where we go with this because we're out of time. Yeah, you have zones of cooling just like we had zones of drying. If you remember those drawings. Yeah, now while I'm thinking about it, when I send it, I'll post the PowerPoint tomorrow that we just looked at, except I'll correct those drawings where the wet grain wasn't labeled and marked right and stuff. There's a couple things there I gotta correct. So that'll be in the corrected PowerPoint. But for cooling, you get similar zones of cooling going on. There's a place down at the bottom of zone 1 where everything's already cool. There's a cooling zone. So there's a cooling zone up here where the change is taking place, and then there's a zone up at the top where no cooling has taken place yet. It's still warm at the top. So in the middle of the process, that's what it looks like. You can see there's a drying zone indicated here. Because what's going on, as I mentioned, during a cooling process, moisture is going to be changing. Typically, it's going to be drying. It's possible that it's a wetting process, but typically it's a drying process, and it affects the temperature right here. The temperature after the air has gone through the drying zone is slightly lower than the temperature of the incoming air. Now what happens, you can see the cooling zone has moved way up ahead of the drying zone down here. Cooling zones moves a lot faster. It takes a lot less air to cool these products off. There's a lot less, basically there's a lot less energy in there than there is moisture compared to what the air can carry. And so it cools very quickly and moves through here. In a drying process that we were just talking about, we actually totally neglected the cooling that goes on initially. It happens so quick compared to the drying process, you ignore it when you're looking at drying. And the way you ignore it is this temperature here that I've labeled as T2, which if we waited just a little bit later in the cooling process, all of the grain above this point would be cooled off to T2. That's the same temperature that we call TG in the drying process. So in the drying process, we were ignoring the fact that for a while, a relatively short time at the beginning of drying, we had all this stuff going on for cooling. Now, if we're only looking at the cooling process, we got to back up and look at that small amount of time we neglected. So that's the basics of how you use those equations. But again, the air is going through a drying process, but we just don't let it go anywhere near completion. The drying zone just gets started. The drying zone's way down the bottom during a cooling process. And we just look at what happens to the cooling, mostly. And last thing here that I mentioned that airflow resistance always comes up in these problems because we're blowing air through the process in any deep bed drying process. And that's a standalone problem that may come up on the exam is looking at the airflow, and it's going to come up in drying problems. The data you need for that is ASAB E272.3, D272.3. That has some equations that on the exam you might not want to use. You might want to use the chart, except there's a problem with the chart that it's raw data for taken in the laboratory that shows 30 to 50% less resistance than actually occurs once you have a large volume that you'd be using in a grain drying situation. You're going to get more than what's in ASA data. There's a little footnote in here that says that. And to find out that difference, the Midwest Plan Service reference, if you look back to that reference list on an earlier slide, I referenced this Midwest Plan Service thing. It gives, that's the one, about the only place you can find values for that. And this chart that's right here on this PowerPoint, I have combined those two and made a new chart. This looks like the chart in ASA data, but it's what I call design values because I've taken into account that extra resistance you get that they'll define for you Midwest Plan Service. And it's done as just a factor. For soybeans here, the factor is 1.3. For corn, the standard factor is 1.5. And you can see for each product here, I've used a certain factor and listed it in parentheses, but this is a factor that's given in Midwest Plan Service. So again, this is one of those charts. You want to use this chart instead of having to combine those two things together if you went directly to ASA data. One of the example problems that will be uploaded tomorrow, I think has a copy of this chart in it too. I'll make sure it does by tomorrow. Of course, this slide right here, you can print it off. It'll be in the PowerPoint that gets uploaded tomorrow. It's the data. I don't know of any other place that this is graphed other than the places where I've done it. Without a graph this way, you've got to put the two pieces of data together and make your life a little more difficult. So, all right, with that, I think I need to wrap up. This, you can look through these slides. This is an example of using these numbers. It's just plug into the equation, calculate pressure drop. The basic approach to a problem like this, if you're doing a design problem, you're going to be selecting a fan for the problem. The examples about aeration of grain. When selecting a fan, you just look at the system curve. That's how the resistance of the material the air is blowing through changes at different airflow rates versus the fan curve, how the fan responds. the point where those two lines intersect is where the fan's going to operate in the system. So, for fan calculations, you've seen this before, and so that's how it's going to work in this case too. The big difference from other situations is the system is going to be this bed of material that if you get the resistance for it, so you're going to get pressure drop off this chart right here. As you look through the example, you see it's pressure drop per foot. So you look it up in the chart and see what's the total depth of material that you have after you looked at pressure drop per foot on the chart. Okay, so that's how I do it. So the last example, I said a while ago, there's an example of an evaporator. That's a more complex example. It's listed as number 8, and then there's an example number 9 in this PowerPoint as it goes on, and that is an example of using this fan selection, using the airflow resistance and everything. That's that example. And so for both of those last two examples, they're in the PowerPoint here. They're also in a separate PDF file that'll get uploaded tomorrow, so you can see, both versions. The PowerPoint may not have as good explanation as what's in the PDF version. You see it both places. So those last two examples are there. So the example of this is there, and I put some final thoughts up here. Again, it's the stuff you've probably heard from others, but just some tips from me for taking the chance. And my last point there is figure out some longer or iffy problems after you've done the ones that you know. I still remember when I took the P exam, it was actually in the days of 4 long problems in the morning, 4 long problems in the afternoon. And after I got done the three I thought I knew how to do, I figured out a 4th problem right there during the exam. So it can be done, I think. Just get all the stuff you know done first. Okay. Any last questions for me? Again, I gave my email address in there, so as you have specific questions of these examples, if you look through those last 2 examples and have questions, you can email me the questions. Okay. Yep, you're welcome for this. Sorry for all the issues with sound. After we had the problems intermittently, I'm thinking I have a loose wire that maybe it started off loose. Seems like after it's loose, I have to mute and unmute to get it, so I better use a different microphone next time I do this. But anyway, again, yeah, send me questions. I've been really busy the last little while before I was getting ready for this, but that's kind of wrapped up, so I should have plenty of time for responding to questions if you have some. So good luck on the exam. Yeah. I'll talk to any of you later if you email me. So have a good night.